Let's talk, Nick, about gravity, but now instead of talking about it as just 9.8 and g, we're going to start to try and generalize it for anywhere in the universe. This is one of Isaac Newton's many discoveries. First of all, let's start with obviousness. Objects in free fall accelerate at what? 9.8 meters per second squared, as long as they're on the Earth. Why? The reason that they accelerate, I'm going to try and get you to think about that 9.8 a little differently now. The reason they accelerate at 9.8 meters per second squared is the Earth has, and here's our new term, a gravitational field strength of 9.8 newtons per kilogram. Clothy, it's not a coincidence that the 9.8 is the same thing there for both. What's Newton's, Clothy, a measure of? What do I measure in newtons? Starts with the letter F. What do I measure in kilograms? Starts with the letter M. So F over M. F equals what? This is acceleration. But what we're saying is this. The reason objects accelerate at 9.8 meters per second squared is because Earth gravity pulls on them with a force of 9.8 newtons for every kilogram of that object. It's a slightly different way to think about that 9.8. We're relating it now to how gravity is acting on every kilogram of mass. The Earth has a gravitational field strength near its surface of 9.8 newtons per kilogram. And that's why objects will accelerate at 9.8 meters per second squared. So up until now, we've been aware of two ways to determine the gravity field of a planet. One way we did last year, where we dropped objects from the ceiling and we timed how long it took them to hit the ground, and we measured the distance, and we used that to try and find A, and we were hoping to get 9.8. If we did it in a vacuum with fancy equipment, we can say, if we're dropping an object, get the obvious one, mg is ma, the m's cancel. And one way to find the acceleration due to gravity is to drop an object, time its free fall, and work out what A is. There's a second way. If you have a scale that's calibrated for newtons, like this one is, you can also hang a known mass on it. And if you take this scale, what's it say in newtons roughly? 10? It's actually 9.8, because this is a 1 kilogram mass. If I go F divided by M, I'll get 9.8 newtons per kilogram. That's another way to measure a planet's acceleration due to gravity without dropping something. Instead, measure how hard gravity is pulling on a known mass. Both of those are great. Both of those are easy. So I wrote here the second way we can find the gravity field at a point. It can be determined by measuring the weight, Fg, of a small test mass, m. The ratio of weight in newtons to mass in kilograms also gives you an acceleration or a gravity field. A spring scale works in this manner. So here's what I want you to realize, and we're going to start to use these kind of interchangeably. Instead of saying, or another word phrase for acceleration due to gravity is gravitational field strength. You could say gravitational field strength was measured in meters per second squared, but I'm going to say it's measured in newtons per kilogram, because it's really the one that comes out of F equals what, and we get the A by itself, newtons per kilogram, which also has to be meters per second squared because they're both accelerations. Okay. Here's the question then. Finding this G, either by dropping an object and timing it, or by letting it dangle from a spring scale, you have to be on the planet to get the G value. How can we figure out gravitational field strength on the moon or other planets? Because, Jan, we had to know what they were before we could build rockets to land on them. All of our Mars probes, none of us have been to Mars personally, but we know what the gravitational field strength of Mars is. That's how we know how strong to build the retro rockets for the landers there. For the lunar landers, same idea. We knew how strong G was on the moon before we went there. The question is, how? And this is what Isaac Newton gave us. Newton found that universal gravitational field strength anywhere depended on two things. Number one, the mass of the object, and you could put in brackets, planet, creating the gravitational field. Bigger planets, stronger gravity. Sorry, I should pick my words more carefully, Keegan. More mass, stronger gravity. Less mass, weaker gravity. And then he also found that it depended on the inverse or reciprocal. Sorry, wrong word there, sorry. He found it depended on the square of the distance from the center of the planet. But he found this one, as this distance got bigger, gravity got smaller. In other words, he said this on the next page. Universal gravitational field, we'll still use a lowercase g, is proportional to, depends on, that symbol there, that little fish means depends on two things. The mass of the planet divided by how far you are from the planet center squared. Problem. Here's the problem. What are the units, Keegan, for mass? What are the units for radius? Kilograms per meter squared is not newtons per kilogram. So to turn this into an equation, we need to multiply it by a conversion factor. In the same way that to multiply, to change minutes to seconds, you need to multiply by what? 60. To change kilometers to meters, you need to multiply by 1/1000th or divide by 1,000. We need a conversion factor. And the conversion factor is capital G for the universal gravitational constant. This is universal gravitational field. Little g equals big G, big M, over R squared. Where big G is, this is on your formula sheet as well, on the page where you have all the constants, where you've got the radius of the Earth, and by the way, in this unit, we're going to be on that page an awful lot. What is big G, Lena? Starts with a 6, I think. It's going to be there somewhere. What I'm really saying is all of you need to find where it is on your formula sheet. What is it? 6.67 times 10 to the negative what? Okay. So to change kilograms per meter squared into newtons per kilogram, what do I need to multiply it by? 6.67 times 10 to the negative 11, and then the units, for what it's worth, are Newton meter squared per kilogram squared. That gives you an answer in newtons per kilogram. 6.67 times 10 to the what? 0.0000000000667. Is that a big number, Nick, or a small number? 0.0000000000667. Nick, is that a big number or a small number? Really small. Newton actually couldn't come up with an experiment to measure it. So what he did, he knew it had to be there, but he didn't know how big it was. He always set up his equations so that big G would cancel out, because I don't know how to find this. I just know it's really small. The reason it's so small, gravity is a terribly weak force. Of the four fundamental forces, right, it's by far the weakest. By far. Oh, Lena, while we're on it, what does big M stand for? Mass of the planet, whatever's sending out the gravitational field, black hole, star, planet, spaceship, whatever is sending out the gravitational field. What does R stand for? Now, you may see some equations put a D there because it's a distance, but I'm going to put an R there because we're going to start to think about things moving in circles around each other. So let's put an R there. Okay. Did I give you that on your formula sheet? I don't know if I did. Now, if you want to, not right now, later on, you can add it to your blue sheet, but I'm actually going to argue I did give it to you on your formula sheet. I just hid it. Because remember, this G is also the acceleration due to gravity. F equals what? Remember that. We'll come back to it. So, notice how small, Nick, big G is. 6.67 times 10 to the negative 11. It's because gravity is by far the smallest of the four fundamental forces in the universe. So, although Newton predicted the need for a conversion factor, big G, its value was so small, he couldn't come up with an experiment to measure it. So he always set his equations up so that the big G would cancel. About 100 years after Newton published this equation, a scientist named Henry Cavendish came up with a way to measure that in 1798. How would you measure something so small, you ask? How would you measure something so small, you ask? How would you measure something... I'm so glad you asked. Put your pencils down, look up. It has cheesy 80s music, so I'm going to mute it, even though I grew up in the 80s. This is the Cavendish experiment. I'll show you what he did. What he realized was if he could somehow write an equation that had gravity on one side equals some other force, and if he knew that other force, he could solve for big G. The problem is gravity is so small here on Earth. I mean, yeah, the Earth creates a big gravitational force. How can you measure the force of gravity between two small objects? So he took two large masses and he put them on a beam and he suspended them from string. So this resolution isn't great, but there's fishing line. Hold it, you can see, kind of barely see, there's some fishing line right there and right there. The point is, this is free to rotate and it's very sensitive. So there's no magnets, no mirrors, no springs, no tricks. Any objects with mass will send out a gravitational field. Right now, you're all tugging on each other with a gravitational field. So what Cavendish did is he put two large lead weights, one right here and one right here. And then he waited. Watch. Slowly, this lead weight pulls on that mass with the force of gravity. See it. There's a time lapse. This lead weight pulls on that mass, and he was able to measure the twist in the rope, and that he was able to calculate the force of. So he was able to say F twist has to equal F gravity. And from that, he was able to get the big G by itself. It's a very clever experiment to do in 1898. If you want to, you can reverse this. So we put the bricks on the other side. We'll see the same thing again. Both objects are attracting each other. Remember, forces come in pairs, so these two objects are pulling on each other with a gravitational force. This one isn't free to move. These two objects are pulling on each other. This one isn't free to move. So ever so slightly. He did this over several days in an enclosed room, not touching it. Let it slowly twist. This is the Cavendish experiment. Very clever. So, when he did that, he found that G was equal to 6.67 times 10 to the negative 11. And he was thrilled because finally, this allowed him to calculate the mass of the Earth. Example 1, the radius of the Earth can be measured using geometry of the sun's rays, and the radius of the Earth is 6.38 times 10 to the 6th meters. Find the Earth's mass using the value of 9.8 for the free fall acceleration. Say what? So Cavendish did this. Little g equals big G, big M over r squared. He got the M by itself. Madison, how will I get the big M by itself? How will I move the big G over? How will I move the r squared over? So he did this. Big M equals G r squared, and then r squared though, so it's not GR anymore, divided by big G. And then he plugged it. We knew the radius of the Earth. We've known that actually for about 2,500 years. A Greek scientist named Eratosthenes did a very clever experiment using the angles of the sun's rays to get how much the Earth must curve by. So he plugged in the numbers. He said the mass of the Earth has got to be, he knew little g. What's the acceleration due to gravity here on the Earth? What's little g? He put in the 9.8. He put in the radius of the Earth, 6.38 times 10 to the 6th, don't forget the squared, divided by 6.67 times 10 to the negative 11. All of you should try typing these in because you're going to have to get very good at your scientific notation buttons during this unit because we're going to be using the actual numbers from the universe and they're just not convenient. So 9.8 times 6.38 times 10 to the 6th, don't forget the squared, divided by 6.67, scientific notation button, negative 11. The answer you're hoping to get is 5.98 times 10 to the 24th. If you don't, later on snag me and I'll show you how to use your scientific notation button. But see if you get that. Mal, get that okay? So did Cavendish by hand, so this took him a long time to do this math by hand. But he wrote this out, 5.98 times 10 to the 24th kilograms. And he sat there just stunned because this was way too heavy from what they'd thought. Up until then, the best way that they could figure out the mass of the Earth, and this is very crude, they literally took shovels of dirt, measured the mass to find an average mass of a shovel of dirt, and then said, okay, how many shovels of dirt would fit in the volume of the Earth? Multiply, there you go. And they got an answer way smaller than this. This number right here was the first indication that it isn't dirt all the way down. What do we think now is at the center of our Earth? An iron core, a very dense and heavy iron core. This, Nick, was the first indication that there's something weird, something different, and not dirt down there. Okay. Oh, by the way, can you find the 5.98 times 10 to the 4th on your formula sheet in the data section, the mass of the Earth? I gave that to you, yes? And also, can you find the radius of the Earth, the 6.38 times 10 to the 6th in your data section? I gave that to you. You're going to be using those two an awful lot. So if you, I don't know what the mass of the Earth is, I will mock you mercilessly. It's on your sheet. In fact, a lot of you will end up memorizing those two this unit because you're lazy. Okay. So that's universal gravitational field strength. You want to find the, oh, by the way, now we can find the gravitational field strength of the moon. Don't write this down, just look up. From your formula sheet, what was big G? $6.67. Oh, I missed the decimal. Times 10 to the negative 11 times mass of the moon on your formula sheet. 7.35 times 10 to the 22. Is that what you said? Okay. Divided by radius of the moon. This is how we knew that the acceleration... Oh, I did this totally wrong, Mr. Dewick. What did I type wrong? Oh, I forgot the squared, Mr. Dewick. Jeez. Squared. Sheesh. Me too. This is how we knew that the gravity on the moon was about 1.6, not 9.8. This is how we were able to design our lunar landers and our moon rockets. You can do a similar thing. Look up the mass of Mars, Nick, and the radius of Mars, and you can find the gravity on Mars. Not 9.8. It's about 3 point something. So this allows us to figure out gravity anywhere, gravitational field strength anywhere in the universe. This allows us to figure out gravitational field strength in orbit somewhere, if we need that for some reason. But having said that, we're going to pause here. We'll pick up with this next class.